Welcome to First Principles Daily, episode 33. Let's run the magic wand number and the idiot index on today's subject. Messages crossed the Atlantic in 2 weeks by ship until engineers treated the ocean floor itself as the medium and moved a word in minutes. Before the electric telegraph, any word sent from London to New York traveled inside a mail pouch on a steam packet that required roughly 14 days to complete the crossing. That 14-day figure already baked in favorable winds and good coal consumption. In bad weather, the same voyage could stretch longer, yet the fundamental limit stayed fixed by the hull moving through water. The binding limit was the physical speed of the hull through water, not the information itself. No amount of clever packing inside the pouch could change how fast the packet displaced seawater or how long it took to cover 3,000 kilometers. Engineers who asked what physics actually required for moving a signal instead of a letter replaced the ship with a copper conductor insulated by gutta percha and laid across the seabed. Once the conductor sat on the ocean floor, the electrical impulse no longer needed to push a hull through waves or wait for coal to be shoveled. The time for a message dropped from weeks to minutes, and the cost structure of moving information changed for good. For centuries, the only proven method of moving a written message across an ocean was to place it aboard a vessel and wait for the vessel to arrive. Ship owners and merchants optimized hull shape, sail plans, and later steam engines, yet the fundamental constraint remained unchanged. The letter had to share the same physical journey as every other ton of cargo. A typical transatlantic crossing in the 1840s still required 12 to 16 days depending on weather and season. That range already reflected the best average performance after decades of incremental sail and engine improvements. The lower end of 12 days was still measured in full days, not hours. The cost of that journey included the ship's capital, crew wages, coal or canvas, insurance, and the opportunity cost of capital tied up for the duration. Because every message incurred the full marginal cost of the voyage, senders accepted that a business letter or diplomatic dispatch would be days or weeks old on arrival. No one questioned the premise that information must travel inside a container that also carried passengers and freight. The container was simply made faster and more reliable. Newspapers printed European news only after the latest packet docked, and currency traders in New York adjusted exchange rates only after the same vessel's mail reached Wall Street. The entire commercial and political rhythm of the Atlantic world was therefore paced by the sailing schedule rather than by the intrinsic speed of an electrical impulse. That schedule was treated as an immutable fact of geography and engineering practice. One objection sometimes raised is that faster clipper ships or more efficient steam packets could have narrowed the gap without new technology. In practice, those improvements still left the fundamental physics untouched. Any vessel had to displace water and contend with wind, current, and storm, so the time floor remained measured in days rather than minutes. Another objection is that optical signaling from shore towers or semaphore chains might have bridged short distances faster. Yet those systems stopped at the water's edge and offered no path across 3,000 kilometers of open ocean. The ship therefore remained the unchallenged default, because every incremental gain in hull speed or reliability still preserved the original analogy that a message is simply another piece of freight. The first principal step was to separate the signal from any physical container and ask what minimum material and energy would be required to propagate an electrical impulse across 3,000 kilometers of seawater. A rough magic wand estimate begins with the conductor itself. Several thousand tons of copper whose commodity value at mid-19th century prices amounted to perhaps a few £100,000 sterling for the entire cable. To see the scale, picture roughly 3,000 tons of copper priced at roughly £100 per ton. That arithmetic alone lands near £300,000. The dominant insulation material, gutta percha, added another comparable sum. Adding armor wires, tar, and the cost of the laying ship still left the raw material floor well below £1 million. The first Atlantic cables, however, were contracted at roughly £1 million each. That contract price implies an idiot index on the order of 2 to 3 when measured against bulk commodity prices alone. To see the ratio clearly, consider the materials alone. Copper at a few 100,000 pounds plus a similar amount for gutta percha, and the rest of the basic components puts the floor somewhere under 1 million pounds. Divide the 1 million pound contract price by that material floor, and the result sits between 2 and 3. The index signals that the dominant expenses lay in manufacturing uniformity, electrical performance, and the repeated failures of early lathes rather than in the copper or gutta percha themselves. The decisive engineering moves followed directly from the physics of signal loss. Gutta percha was selected because it remained flexible and non-conducting after prolonged immersion, unlike earlier rubber compounds that absorbed water. The cable was built with a central copper core surrounded by several layers of gutta percha, then wrapped in hemp and iron armor wires to survive the laying process and seabed abrasion. Early cables failed because the insulation was too thin or because the conductor resistance was too high for the voltage that could be applied without breakdown. Each failure revealed a specific limit that the next design iteration addressed by increasing insulation thickness or conductor cross-section. The 1858 cable carried a detectable signal but degraded within weeks because its gutta percha layer was insufficient to prevent leakage. The 1866 cable used a thicker dielectric and a larger copper section, allowing reliable operation for years. Laying the cable required solving the additional problem of paying out 3,000 kilometers of heavy rope under controlled tension from a moving ship. The steamship Great Eastern was rebuilt with enormous cable tanks and linear braking engines so that the cable could be released at a speed matched to the ship's progress. Each of these steps attacked a concrete physical bottleneck rather than copying the practices of overland telegraph lines. A common objection is that simply scaling up landline techniques, thicker wire, and more battery voltage should have sufficed. In reality, the seawater itself acted as a parallel conductive path that drained the signal unless the dielectric was thick enough and uniform enough to block leakage over the entire length. Another objection is that the high idiot index reflected only temporary teething problems of a new technology. Yet the cost structure remained dominated by the need to achieve electrical continuity and mechanical survival in a single continuous deployment. Once those constraints were met, later cables reused the same core design with only incremental refinements in armor and payout machinery. Once the 1866 cable entered commercial service, a message that had previously taken 14 days could be transmitted in roughly 10 minutes of electrical transit time. Manual encoding and decoding added further minutes at each end. The cost per word fell from the equivalent of several days' wages for a courier to a few shillings once traffic volume rose. Stock exchanges in London and New York began to move in near real time, and newspapers could print same-day foreign news. The idiot index of the cable itself dropped as manufacturing yields improved and as subsequent cables reused proven designs. Yet the absolute cost of each new cable remained high because the laying operation still required a specialized ship and a multi-month expedition. Early cables also suffered from low bandwidth. The electrical characteristics of the long conductor limited signaling speed to a few words per minute until loading coils and later electronic repeaters were introduced. Those limits were accepted because the alternative, continued reliance on ships, remained slower by orders of magnitude. A cable whose price was driven mainly by the need to survive a single high-risk deployment rather than by the copper inside it, revealed that the expensive step was not the conductor, but the process of placing it. The same principle applies whenever a new physical path must be created before information or material can flow. The first workable path carries the full cost of proving that path is possible. Tomorrow, the show returns with another concrete case in which someone measured the raw material floor and then removed everything that stood above it. What single constraint would have to be removed next for transoceanic communication to approach the speed of light itself? That's First Principles Daily for today. If this changed how you see what things cost, share it with someone who'd appreciate it, and subscribe wherever you listen. I'm Patrick in Vancouver, one example or one opportunity every day. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.
I'm about to prove